One planet in our solar system breaks a rule that almost never fails, a rule so fundamental that scientists rarely question it. A rule followed by every other planet we know. Every planet in our solar system spins in the same direction, not by chance, not by coincidence, and not because they choose to. Planetary rotation is decided long before a planet is fully formed. It begins at the birth of the system itself. When a star starts to form, it doesn't appear alone. It emerges from a vast cloud of gas and dust, collapsing under gravity. As that cloud collapses, it begins to rotate, and as it rotates, it flattens into a disk. Inside that rotating disk, everything inherits motion. The dust, the gas, the material that will eventually become planets. This shared motion is unavoidable. It's the result of conservation of angular momentum, a basic principle of physics. Once that motion is established, it dominates everything that forms afterward. Because of this, planets don't spin randomly. Their rotation is locked in early, shaped by forces far larger than the planet itself. And once a planet forms, that direction of rotation almost never changes. In our solar system, this pattern is remarkably consistent. Mercury spins one way. Earth spins the same way. Mars follows the same direction. Jupiter, Saturn, Uranus, Neptune all rotate according to the same inherited motion. There are differences, of course. Some planets spin faster. Some spin slower. Some are tilted at extreme angles. Some rotate almost on their side. But despite all these variations, the direction itself remains the same. This consistency is not a coincidence. It's one of the foundational assumptions used to model how planetary systems form and evolve. It allows scientists to reconstruct the past and predict how systems behave over billions of years. When astronomers observe distant stars surrounded by protoplanetary disks, they expect to see the same behavior, and almost always they do. Planets forming from rotating disks, inheriting the same direction of motion, following the same rule. That rule is so reliable that it's rarely questioned. It's taught early, accepted quickly, and reinforced every time a new planetary system is observed. Almost nothing is powerful enough to change the rotation of a planet once it forms. To reverse that motion, you would need an enormous amount of energy, enough to overpower the momentum of an entire world. That kind of event wouldn't be subtle. It wouldn't be quiet. It would be violent, catastrophic, and impossible to ignore, which is why, for a long time, scientists assumed that a planet spinning the opposite way simply didn't exist. Planets spin the way they're born. That's the rule. And rules like this don't break easily. They don't break quietly. There is one planet that does not follow that rule. It doesn't spin slightly differently. It doesn't rotate at a strange angle. It doesn't wobble or drift out of alignment. It spins in the opposite direction. If you were hovering above its north pole, you would see the sun rise in the west and set in the east. Day and night unfold backwards compared to every other major planet in the solar system. This is not a trick of perspective. It's not an illusion created by orbit or camera angle. The rotation itself is reversed. For a long time, this made no sense, because changing the direction of a planet's rotation is not like nudging an object in space. A planet is not a spinning top. You can simply flick the other way. It carries enormous angular momentum, energy stored in motion that resists change. To reverse that motion, something extraordinary must have happened. Something powerful enough to overcome the momentum of an entire world. When scientists first confirmed this planet's backward spin, the reaction was not excitement. It was discomfort. Because the moment you accept that a planet can rotate backwards, you are forced to question assumptions that almost never fail. This wasn't supposed to be possible, and yet, there it was. Unlike other planets, this one completes a single rotation extremely slowly. A single day on this planet lasts longer than its year, and the direction of that slow rotation is fully reversed. This alone would make it an anomaly, but the deeper scientists looked, the more unsettling the picture became. A backward rotation doesn't exist in isolation. It affects how sunlight is distributed across the surface. It changes atmospheric circulation. It alters how heat is trapped and released. The planet's climate behaves in ways that don't resemble anything else in the solar system. Temperatures don't follow simple patterns. Winds don't move the way models predict. The atmosphere itself behaves as if it is fighting against the planet beneath it. At first, researchers searched for simple explanations. Measurement errors, faulty assumptions, incomplete data. But the observations held. The planet really does spin backwards, which means that at some point in its history, something happened that was powerful enough to either reverse its rotation entirely or prevent it from ever spinning the correct way to begin with. Both possibilities are deeply unsettling, because if the planet formed normally and was later forced into reverse, then the early solar system was far more violent than we like to imagine. And if it formed already spinning backwards, then our models of how planets inherit motion are incomplete. Either way, the exception is real. And once you accept that, another question becomes impossible to ignore. The backward spin is not just a curiosity. It is a clue, a signal that something about this planet's history went catastrophically wrong. And that wrong turn didn't stop with its rotation. Once scientists accepted that the planet's rotation was truly reversed, the question stopped being how strange this is and became how far the consequences go. A planet's rotation controls far more than day and night. It shapes climate, atmospheric circulation, and the way energy moves across the surface. Change the direction of that rotation, and you change the entire system. On T's, planet's sunlight behaves differently. Heat builds slowly and unevenly. Instead of being distributed smoothly around the globe, it becomes trapped. Over time, that imbalance grows. The atmosphere begins to circulate in unexpected ways. Winds no longer follow familiar patterns. Instead of stabilizing temperatures, they amplify extremes. This creates a runaway effect. Heat builds faster than it can escape. The surface grows hotter, and the atmosphere, instead of protecting the planet, begins to work against it. This is where the backward rotation stops being a curiosity and becomes a warning. Because when scientists model this planet's climate, they don't see a stable system. They see one that slowly spirals out of balance. Temperatures rise beyond what the planet should be able to sustain. The atmosphere thickens. Pressure increases. Eventually, conditions become hostile to anything resembling stability. And here's the unsettling part. The planet didn't start this way. Early in its history, it may have been far more similar to Earth than we like to admit. Comparable size, comparable composition, possibly even liquid water on its surface. But something changed. Whether it was a catastrophic collision, a violent early atmosphere, or a combination of both, the result was the same. The planet crossed a threshold. Once that happened, there was no easy way back. The backward spin altered the climate. The altered climate destroyed the atmosphere's ability to regulate heat, and the loss of regulation pushed the planet into a runaway state. This sequence matters because it shows how fragile planetary balance really is. A single deviation, one broken rule, can cascade into total transformation. Scientists don't study this planet out of curiosity alone. They study it because it represents an extreme outcome of processes that exist everywhere. The same physical laws apply to Earth. The same forces shape atmospheres. The same feedback loops govern climate stability. Earth is not spinning backwards, but it doesn't need to. The lesson here isn't that Earth will become this planet. It's that planetary systems are more sensitive than we often assume. When balance is lost, recovery is not guaranteed. This planet is what happens when a world takes a wrong turn early and never corrects it. And the backward spin was only the beginning. Because when scientists looked deeper, they discovered something even more disturbing. This planet didn't just break the rules of rotation. It lost something essential, something that almost every stable world needs to survive. In the next video, we'll look at how this planet lost its atmosphere. If you want to follow the full sequence, subscribe.